Good morning, students. Today we are going to see the topic of rotational spectroscopy. So, when a molecule has permanent dipole moment, it generates an electric field which can interact with the electric component of electromagnetic radiation. As a result, absorption of radiation takes place in microwave region. Hence, rotational spectroscopy is also called as microwave spectroscopy. Generally, a 1-mark question is asked on this. According to quantum mechanics, rotational energy levels of the molecule are also quantized. It is important. Similar to electronic energy level, hence absorption of rotation in microwave region leads to the rotational excitation of molecule leading to absorption signal. Useful information about the bond length can be obtained from the spectrum. So basically, rotational spectroscopy is used to find bond length of the molecule. Most important condition for getting rotational spectrum is that the molecule should have permanent dipole moment. Hence, the homonuclear diatomic molecules like H2, N2, etc. cannot be studied by using this technique. Heteronuclear diatomic molecule like HCl, CO, NO, etc. show rotational spectrum in gaseous state. Now, it is important. What is the meaning of permanent dipole moment? When molecules possess del positive and del negative charge, it is considered as that molecule have permanent dipole moment. In case of H2 and N2, this type of del positive and del negative charge distribution cannot be possible. That's why this homonuclear diatomic molecule does not show a rotational spectrum. Now we are going to see classification of molecule. An important parameter governing rotational motion is moment of inertia. Let us assume that the moment of inertia about x, y and z axes are Ia, Ib and Ic respectively. On the basis of relation between the moment of inertia along various axes, molecule may be classified into 4 groups. This is equivalent to classifying molecule according to their shapes. Now, first category of molecule is linear molecule. For linear molecules, Ia, that is moment of inertia along x-axis is 0, Ib is equal to Ic cannot be equal to 0. The examples of diatomic molecules are CO, HCl and triatomic molecule like CO2, COS. So now we are going to see example of COS. Now just see. If it is your sulfur atom and if it is your oxygen atom and carbon atom is present at the center, what happens if I rotate this molecule along its x-axis? Let x-axis is passed from here to here. So what going to be happen? There is no change. So that's why moment of inertia along x-axis is 0. Now let this is your y-axis. What happens if I rotate this molecule along y-axis? So we clear cut see that there is change of position of sulfur and oxygen atom. That's why Ib cannot be 0. Now let consider it is your z-axis. So it is your original position, and if I rotate this molecule like this, there is also a change in the position of your sulfur and oxygen atom. That's why IC is also not equal to 0. Second category is of symmetric top molecules. Example of symmetric top molecule is CH3Cl. In this case, Ia cannot be 0, Ib is equal to Ic, that is also not equal to 0. Just see here what going to be happen in this case. This is the structure of CH3Cl. This structure is somewhat similar to that of your inverted umbrella. So this is your stand of umbrella or handle of umbrella. What happens if we rotate this molecule along x-axis? It is clear concept that if we rotate this molecule along x-axis, only the position of hydrogen changes. So that's why Ia cannot be 0 in this case. What happens if we rotate this molecule along y-axis? So from this geometry, we clear cut see that if we rotate this molecule along y-axis, Cl comes in this plane and all these group goes in that plane. Cl comes on left hand side and this methyl group goes on your right hand side. So Ib also not equal to 0. What happens if you rotate this molecule along z-axis? When you rotate this molecule along z-axis, it is clear cut see that Cl again comes on right hand side and this methyl group goes on your Cl comes on your left hand side, methyl group goes on right hand side. So it means that Ic is equal to Ib, which cannot be equal to 0. Third category is asymmetric top molecule. Most of the molecule comes under this category. When all the three moments of inertia are different, that is Ia cannot equal to Ib, cannot equal to Ic, the molecule is an asymmetric top. So just see example of asymmetric top molecule is methyl alcohol, CH2, CHCl, water, etc. Just see in this example, water is taken. So what is going to happen if we rotate this molecule along your x-axis? So let here is oxygen, here is hydrogen, here is hydrogen. What happens when we rotate this molecule along x-axis? So it simply means that your both the hydrogen comes upward. So Ia cannot be equal to 0. So now what happens when we rotate this molecule? It is your previous position. If we rotate this molecule, let this is your y-axis. What happens if we rotate this molecule along y-axis? This hydrogen comes on this plane. Just see, this hydrogen come on first present in right hand side. This hydrogen is present on left hand side. When we rotate it, what going to be happen? Position of hydrogen interchange. Now let's consider it is your y, it is your z axis like this. If we rotate this molecule like this, what going to be happen? We got total different new configuration or arrangement of atom. So that's why Ia cannot equal to Ib, Ib cannot equal to Ic in a symmetric top molecule. Next type is spherical top molecule. When a molecule have all three principal moments of inertia identical, that is Ia is equal to Ib is equal to Ic. Example is methane SF6. So just see, this is the example of what happens when we rotate this molecule along y-axis. Just position of this hydrogen interchange. It is just like this. And what happens when we rotate this molecule along z-axis? Position of hydrogen just interchange. So Ia is equal to Ib is equal to Ic. Now we are going to see diatomic molecules as a rigid rotor. Due to the rotation, a centrifugal force develops in a molecule. Due to this, the bonds gets elongated. Such a molecule is called non-rigid rotor. For understanding rotational spectrum, we will assume that bond length does not change during rotation. Such a molecule is called rigid rotor. Students should note that it is only hypothetical case. It is not actual case. Consider a diatomic molecule with the two atoms A and B having masses m1 and m2 respectively. So just see here, this is your atom A, this is your atom B. Atom A have atomic mass m1, atom B have atomic mass b2, and it is a diatomic molecule. The distance from center A to that of center of B, it is equal to r0. Let the distance between them is r0. If the molecule rotates about an axis through center of gravity, that is G, if we rotate this molecule along center of gravity, and r1 and r2 are distance of the two atoms from the center of gravity respectively. So distance between G to A is r1 and G to B is r2. About the center of gravity, we can write m1 r1 is equal to m2 r2. But from figure we can write r1 plus r2 is equal to r0. So one can simply write r2 is equal to r0 minus r1. Put this value of r2 in this equation. So by putting this value and by solving this equation, one can write r1 is equal to m2 divided by m1 plus m2. This whole thing is multiplied by r0. Similarly, a value of r2 can be written like this. Now, the moment of inertia about G is given by I is equal to M1 R1 square plus M2 R2 square. So now put the value of R1 and R2 into this equation. So this is the value of R1 in term of R0 and this is the value of R2 in term of R0. By putting that value in this equation, we can solve this equation and we comes I is equal to M1 multiplied by M2 divided by M1 plus M2, and this whole quantity is multiplied by R0 square. Now the quantity M1 multiplied by M2 divided by M1 plus M2, it is denoted by new constant, that is mu, and it is known as reduced mass of system. So I is equal to mu R0 square. Rotational energy of such a system is given by Ej is equal to half I omega square. Just multiply and divide this equation with I. So one can write I omega square divided by twice I. But I omega is equal to L. So we comes with L square divided by twice I, where L is known as angular momentum, I is moment of inertia, omega is angular velocity. Now it is important, according to quantum mechanics, angular momentum is quantized. It is very important. And according to quantum mechanics, angular momentum is equal to under root of J into bracket J plus 1 multiplied by H divided by twice pi. This is the value of angular momentum according to quantum mechanics, where J is called rotational quantum number having value 0, 1, 2, 3, etc. etc. Substituting equation 4 in equation 3, that is, we have to just put value of L into this equation. So we comes with Ej is equal to h square divided by 8 pi square I into bracket J into bracket J plus 1 bracket close. Now what this E denotes? This is the energy of rigid rotor. Now we can put a various value of J for various energy level. So for J is equal to 0, we comes E0 is equal to 0. For J is equal to 1, energy of first level, it is comes as twice h square 8 pi square I. For J is equal to 2, energy of second level is calculated as 6h square 8 pi square I. For third energy level, J value is 3 and it comes as 12h square 8 pi square I. Student should note that h square is a Planck's constant. So if this quantity is constant, that is h square 8 pi square I, if this value is constant, we just see that what going to be happen. 2 multiply by this constant value, 6 multiply by same constant value, 12 multiply by same constant value. So one can say that as the number of J increases, energy is also increases. So just see, first energy level value is 2 multiplied by this constant thing. For second energy level, this value is multiplied by 6. For third energy level, this value is multiplied by 12. So as the value of J increases, separation between energy level is also increases. This clearly shows that the value of J goes on increasing, the separation of energy levels also goes on increasing. The frequency corresponding to various energy level can easily be calculated. So we know that E is equal to Sc by lambda, which is also equal to Sc by nu bar. What is a nu bar stands for? It stands for wave number. So this is the equation for energy level, and it is also energy. Since left hand sides are equal, one can compare right hand side of these two equations. So one can write Sc by nu bar is equal to h square 8 pi square I into bracket h bracket close into bracket h plus 1 bracket close. After solving this, we comes with nu bar is equal to b into bracket j into bracket j plus 1 bracket close, where b is equal to h 8 pi square IC is called as rotational constant. In our next video, we are going to see selection rule for rotational spectroscopy. Thank you very much.